Hello everybody, this is me Khalid Mehraj Malik over again here with a new video today. Friends, we are going through the magnetism unit of electrical engineering. And only previously we have learnt about inductances. So taking that further, today we shall study about series inductances and parallel inductances. Okay, that's our topic of today. Okay. The topic is, in fact, we have small two topics: series inductances and parallel inductances. First of all, let us discuss series inductances. Series inductances. Much like the resistances in series, inductances can also be placed in series like this. Inductance 1 and inductance 2. Okay. The self inductance of this first one is, say, L1 and this has L2. Okay. And suppose both of them have a mutual induction M. Now here we have two cases. If the magnetic flux in this first inductance has the same direction as that of the magnetic flux in second one, like this. In the first one we have the lines passing like this, direction be like this, and in the second one the direction be like this, the same direction. Then they are called as mutual aiding connections. Mutual aiding series connections of inductances. Mutual aiding series inductances. In this case, friends, the total inductance made by those two, see, this one is self inductance of first one, self inductance of second one, and this one is the mutual inductance in between those two that we have already discussed. So what will be the total aggregate inductance between those two if those are the aiding connections? Then L will be, total aggregate L will be L1 plus L2 plus twice of mutual inductance between them. Okay. Say this one has the direction of magnetic flux lines like this, but in this one, say the direction of magnetic flux lines is opposing, then what will happen? What will happen in that case? This will be case first. This be case second. Okay. In the second one, we take up now opposing series connections. Series inductances, opposing series inductances. In this case, in the first case, when the flux lines of each of those two inductances had the same direction, in that case, mutual inductance between those two, that was aiding the self inductances. Aiding the self inductances means all the three inductances, whether mutual or self inductances, they had the similar sign. M was also positive, L2 positive and L1 positive. But when the direction of the flux lines in those two inductances is opposite and they are put in series, what happens, the mutual inductance between those two, that opposes the individual self inductances. Okay, what will how will we denote that? Okay, here L is equal to L1 plus L2 minus 2m. What will this minus sign denote? That m is opposing mutual inductance between those two is opposing the individual self inductances, and this gives rise to the total aggregate inductance like this one, and this will be lesser than the earlier one. Okay, this is the series inductances. Okay, one more thing, if those two inductances are in series, the current will be same. Say current I will flow from here, the current I will leave, okay. But for the voltage, total voltage lies between those 2 points. The drop for this will be different, why? It could be that those two inductances don't have the same length, although they may have the same cross sectional area, but they may not have the same length. If this one is longer and this one is shorter, this means that the inductance of this one will be different to that of this one. This one is L1 and this one is L2. Accordingly, the voltage drop across this one will be different, and the voltage drop across this one will be different. The current is same, but the voltages across those two are different in series. Same applies to the case first and same applies to the case second. And the total voltage is given by, this is the general formula for voltage across inductances. V is equal to, say we have taken this L aggregate, whether for one inductor only or for two or more series inductors. L di by dt. Time derivative of current, say those two are some metal coils. Those two are simple metal coils. What makes them inductances? What shapes them into inductances? That is the changing current. With time that creates a changing magnetic field, and that changing magnetic field induces flux lines between those metal coils and makes them inductances. So we have this aggregate inductance multiplied by time derivative of current. This gives the voltage across inductor. Okay, coming upon parallel inductances now. Parallel inductances. Say we have two inductances in parallel like this. Okay, the current flowing from here be I. Which current? Not static current, but time variant current. That be I. That is bifurcated into two branches, I1 and I2. the voltage across both those two inductances, that will be same because they are tied to the same ends, they are tied at the ends, so the voltage will be across those two ends. The voltage across those two will be same, but the current will be different according to the length of those inductors or the parameters of those inductors, we can say. Okay, that is one another thing. But let this has L1 as self inductance, L2 as self inductance here, and the mutual inductance between them is M. Again same case, parallel case first. Parallel aiding connections. Parallel aiding connections. In that case, what will happen? The total inductance between parallel aiding connections means aiding the flux line, the direction of the flux lines in this one and this one, the direction will be same, they will be aiding one another, and this mutual inductance that will be aiding the individual self inductances. Okay, so what do we infer from here? L is equal to total inductance, L will be equal to L1 L2 minus 2m minus m square upon L1 plus L2. Parallel aiding connections, m will be plus because it m is aiding L1 and L2 in the parallel aiding connections, plus 2m. Yes, this is the formula for parallel aiding connections of inductances. In case of case second, parallel opposing connections. Over again, what does this mean? The two inductances are in parallel, but the flux lines in this and flux lines in this, they don't have the same direction, they are in the opposite direction. Flux lines are in the opposite direction. Those two inductances are in parallel, but the effects of both those two, they are opposing one another, and the mutual inductance between those two parallel inductors, that is opposing the individual inductances. Okay, so in this case the formula will be L equals to L1 L2 minus m square upon L1 plus L2 minus 2m. Here what do we see? In the series case, in the series aiding case, the inductance, aggregate inductance was more than that of the series opposing case. Okay, but in parallel aiding connections, parallel aiding case and parallel opposing case, the parallel opposing case aggregate inductance is more than that of the parallel aiding case. Here the inductance is less, aggregate inductance that we got, that is less, and here it will be more when those two are in parallel. Okay, that is done. That was a small portion having two small subtopics. In the next section we shall be studying about magnetic hysteresis and eddy currents. Okay, thank you very much.